Hello, everyone. This is Professor Jeff Wilkerson at Luther College, providing a very, very brief introduction to data handling. And this is a video to accompany astronomers as observers and experimenters. It's published by Kendall Hunt. This laboratory book, this laboratory exercise book for introductory astronomy courses. And we want to think about handling data and what we do to handle data. This is a very, very cursory overview. Look at this. You can go as deep into this topic as you would like to go, or not. And we want, but for me, it's important for a couple of reasons. One, we've emphasized again and again that we make observations of the night sky, we make measurements in the laboratory. We have to turn those measurements into some kind of model of the physical system, model of the universe, a star, stellar evolution, the galaxy, how galaxies evolve, whatever this is that becomes a model of the entire universe. And so we need to do that. And how we do that, there's how astronomers, there's a playbook. There is a rule book that says this is the way you probably want to go about handling data. This is a good practice. But there's no one way to approach any data set. And you can take from all of the good practices and build your own good practices and build your own statistical analyses. And you get in there. And so astronomers are really involved in deciding how they're going to look at the data, how they're going to process the data, and what they're going to do with the data. So let's talk just a little bit about how we want to think about doing some of this. And the one way. So let's use an example of the. Well, let's start with this. Let's say you just make a single measurement, or just two measurements, or something like that. So in the exercise where you measure the diameters of Pluto and Charon, you might make two measurements of the diameter of each of those objects. You'd average those, but trying to understand the uncertainty in averaging those isn't going to help you very much. And so one of the things, so we want to practice this because it's an important part of the astronomical process. So we want to model the astronomical process, but it also might be that as you work through this, you want to develop skills at data handling, and you might want to push much further than I'm going to suggest in this video as you do this. And so you might want to be thinking about this in different ways. So you can have different reasons for wanting to do this, but certainly it's an important part of the process of science. And if we want to model that, if we want to think about how human beings have used observations and experiments to build these models, then this is probably important for us to do a little bit to get that feel. So we're doing that. If we think about that, measuring the diameters of Pluto and Charon, as we talked about, it's probably important to understand what the uncertainty, have some estimate of what the uncertainty in our measurements are. And we could do that by taking a bunch of measurements of the same thing and averaging them, and then often saying, well, the mean is our best estimate of what this value is. And our uncertainty is based on the standard deviation or the standard error, the scatter in the data divided by the square root of the number of points. So that's a statistical approach to finding the uncertainty and a value. In the case of the Pluto-Charon lab map, we fit a line here and we fit a line here, and we measure a time right there. We might want to know, so our best estimate is that is where those lines cross is going to be the time of what we call a contact point in there. But we might say our slope could be this big or this big. What's the uncertainty in the slope of this line and in this line? So the crossing point could be anywhere in a region like this. And say that's the uncertainty is anywhere in that region could be the uncertainty of the timing right there. And that might be good enough for us to do a band like that. Or it might not. We can push that as far as we want to go. So in any individual point, as you're working through the exercises in this book, it's worth thinking about what the uncertainty is. If the slope changed, if I have data and I fit a line and the data's got scatter in it, let's say, is that line consistent with those? And is that line consistent with those data points? There are real technical ways to do that, and maybe you want to find the uncertainty in those slopes, the one standard deviation uncertainty in those slopes, and by all means do that if you want to do that. But otherwise, you might just say, well, this line could cross this other line anywhere in this region. And so that's the uncertainty in the timing of T1 of what we're calling in that exercise. So you built an uncertainty in time. What we're doing here is to say time is across this axis and signal value is up here. I should be clear that you maybe haven't looked at that exercise. You probably haven't looked at that exercise, so you don't recognize that's what's going on. And so if this is a graph of signal versus time, this is what we've got. So let's back up another step. We do a lot of work in this textbook practicing making graphs. And graphs are very valuable tools for us to visualize quickly what a data set looks like, what points might be trouble, what points might be valuable points, what something is doing. So for example, we have a vertical axis and a horizontal axis. In this particular exercise, we plotted signal as a function of time. And we call that a light curve for something. We could have plotted a lot of other things in there, different exercises throughout this textbook. We'll have you plotting different things on the vertical axis and the horizontal axis to try to get a sense of this. For example, you will plot the star charts that are in the back of the lab book are basically graphs, their declination as a function of right ascension. It's a graph of the celestial sphere. And in the exercise on determining the mass of the moon, you plot an x-coordinate and a y-coordinate position, a location of the satellite that's orbiting the moon. So you have this satellite that's orbiting the moon, and you plot the location. You have an x-coordinate and a y-coordinate that are based on radii of the moon. You have the moon at the center of the coordinate system based at the center of the moon, and measure how far away you are in one direction and another direction from the center of the moon. And you plot an orbit that looks like that. So hopefully as you work through these exercises, you get better at doing graphical analysis and understanding what those can tell you about the nature of the system that you're looking at. So that's one thing that we're going to do here again and again. We talked about fitting a line here, so let's talk about that just a little bit. One of the things you want to be very careful of is this variable and this variable may not be linearly related. So you don't necessarily want to go fitting a line to every single data set that you see. It's human inclination. Humans want to do that. And in some cases, it's valuable even if they're not linearly related. If you're not making a physical model of the system, you're just using that fit to find what we would say empirically, to find a trend, then you could say, I want to know, is this signal growing or shrinking with time? Fitting a line, even though that's not really a line, even, you're going to imagine this being a curve up like this, the line's still going to tell me the trend is, if there's a positive slope in that line, it's going to show me that that's upward. And that might be valuable to you, even though you know that this data isn't linearly related. Just be clear about that and be careful about that. You might be better off fitting a different kind of function to that if you really want to know what the relationship between signal and time is in that case. So one of the things is, if you do have a curve like that, where it curves up, over a narrow enough region, you can probably get away with fitting a line and do okay. And you can break this thing down and to have a slope here and a different slope here and a different slope here, and do that kind of analysis. Think about how you want to do that with some of these exercises. If you want to go down that route, you can. You can expand these things out to do that. We haven't in the text. We haven't written a lot of this kind of analysis into it. We leave that to you to expand on if you want to. We don't want to make it too challenging up front. But certainly there are places you can expand on all of these things. Let's, while we're here, let's go ahead and talk about a slope of a line. And to say the slope of a line, you fit it like this. That's going to be your intercept. And your slope is going to be the rise over the run, like this. And you want to draw your line so that it doesn't necessarily hit all the data points, but this data point's a little below the line, that data point's a little above the line. You want to average it out so they're above and below the line. If you got software to do this for you, boom, let the software do this for you. By all means, let the software draw this graph in your software, construct this graph. Let the software tell you what the slope of that line is. So in any event, we have a delta y over a delta x. So slope equals delta y over delta x. Pick 2 points on the line, not data points, because the data points might or might not fall on that line. They're a little bit below, and that's a little bit above. And so you want to pick 2 data points, 2 points that are on the actual line itself, not a data point that's in there, and calculate this delta y over delta x to get you the slope. The equation of your line is y equals mx plus b. M is the slope. B is the intercept, which is that value right there where your line crosses the vertical axis. Now, in this case, y and x don't really mean that much to us. X is time for what we wrote here, and signal is on the y-axis. So the better way to write that equation is to say signal is slope times time plus intercept. Okay? And that might tell you how your signal's growing with time, or in this case, how it's shrinking with time as you're going into an eclipse and an eclipsing binary. Again, whatever you plot over here is great in order to do this. And you want to figure out what that rise over run is. Again, there are technical ways you can find the uncertainty in that slope, what the 1 standard deviation uncertainty is, for example. And if you want to go down that route, you can expand a lot of the exercises in this book in order to do that, to do more technical uncertainty analysis with your data. We don't have it written in there, but I would certainly encourage you to do it if that's where you are with the data processing and what you're doing. If it's not, don't worry about it. So in any event, this is one of the things we're going to be doing with the graphs like this. So let's talk about let's think about the exercise 12 in the lab book is finding galactic distances with the Hubble elementary law. And so let's do an introduction to that here right now. There'll be a separate video for an introduction to that activity. But to say, if we measure the distance to a galaxy and its recession velocity, we should be able to use this Hubble elementary law to say that the velocity of recession is equal to the Hubble constant times distance. And so that Hubble constant times distance is a linear relationship. So if we plot v as a function of distance to the galaxy, we should get a line. And that line should have a slope. We draw a best fit line that goes through there. Again, let the computer do it. If a computer, you got a software to do it for you, but draw a best fit line so you got some points above and some points below the line. And then find the slope. And that slope is going to be delta V over delta D is going to be H naught. That's your Hubble constant. Okay? That's a great way to find the Hubble constant. You've got a data table in that exercise, and you've got a lot of different points to plot on here in order to do that. That's a very good way to finding that. Now, there's another way you could have analyzed the data in here. There's not one way. And in an ideal world, you would analyze the data 15 different ways and see how consistent they are with one another and really try to pull this thing apart. You do that as much as you can. Don't trust any one analysis. You want to be careful about that, and you really want to dig into this. But at the same time, there's 168 hours in a week, 52 weeks in a year, and only so many years in an astronomer's career. You can't spend all of your time. You have to, that's part of the magic of doing a project is decide when you've done enough to trust what you have and move forward. And so this is the case here to say, you find the slope of that line is a great way to do it. Another way to do it would have been to just say each data point that's in the table in exercise 12 can be used. It has a distance and a velocity. You can say H naught is equal to V divided by D, the velocity divided by the distance, and you get an H naught value. Notice that these things have units. Okay, velocity is measured in kilometers per second, for example, and distance is measured in megaparsecs. So kilometers per second divided by megaparsecs, H naught, Hubble constant, has units of kilometers per second per megaparsec in this case. So whatever units we have to go along with the algebra that we do right there. So do note that. So this gives you could calculate this point by point. And if I don't remember how many, I didn't look this up before we started this video. I don't remember how many data points we have in there for you measuring the Hubble constant. But if you measure the Hubble constant 10 different times, you're going to have 10 different values of H naught. Boom, 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 and they're going to be each different value with measured in kilometers per second per megaparsec. So a perfectly valid way to do that exercise is to measure that 10 times that way and find the mean. Okay, so find the mean H naught from the individual measurements and compare that to the slope that you get over here. There are advantages and there are disadvantages to each of these approaches. Neither approach is right, neither approach is wrong. They're just ways to access the data, to think about the data. You find the mean, and the mean is just going to be the sum of all 10 of these, if there are 10, divided by 10, or 12, if there are 12, divided by 12. You just sum them up and divide by the number. It's going to be the sum of all your individual H naught values divided by the number of your individual H naught values. And that's great. My guess is, I didn't actually do this, but my guess is with the data that you have in that exercise 12, you're going to get a mean H naught here that's pretty close to the slope that you have there. Interesting to see what the difference is. Okay. Now, in this case, we suggested trying to fit a line to say, well, what's consistent with your data points? A slope of that and a slope of that, and find a minimum and maximum slope and use that as your uncertainty in the Hubble constant. That's one approach to this. Again, there's a statistical way to do that, to find the uncertainty in the slope if you have a computer particularly fitting that line for you. Here, the uncertainty is going to be something called the standard deviation divided by the square root of the number of points that you took. So if you have a code, if you have Excel or something like that, that you plug this into, or you use your calculator, it will tell you that standard deviation. And you can get the uncertainty that way. I'm not necessarily recommending you do it. You do it or you don't. I'm just saying this is a way to go in and do that, to understand that there is a way to think about what those uncertainties are in your measurements. Now, so for example, if there is an intercept, if there's some bias in your measurements, this equation tells us there is no intercept. There would be a plus b out here, but there is no plus b. So we would expect a galaxy that's 0 megaparsecs distant from us to have 0 velocity. But there might be a bias built in there, and that bias might have to do with the internal motions of the galaxies within a cluster. It might have to do with the way we're making and processing the data. So you might actually have an offset. If you have an offset, this technique will allow you to subtract out that offset, and the slope is going to give you a good measure of the Hubble constant. If you have an offset here, you're not subtracting that offset out, and you're going to get a biased measure of the Hubble constant. Okay, so you see how how in that case the slope might be better than the mean approach. The mean approach is also going to be highly susceptible to a single point that is an outlier point. That single point that's an outlier point might really change the mean significantly, and it will raise the standard deviation significantly. So if you have one point that was a mismeasurement, somebody just wrote something down wrong, or something got transcribed wrong, or something along those lines, then you can have a problem here. If that point, here's an interesting thing about doing the linear fit. If that point's in the middle of your data set, it probably doesn't affect your linear fit very much, and you're a little bit more robust to those outlier points. If that outlier point is out on the end of your linear fit, it can change your linear fit a lot. That tail can wag that dog. It can shift that up. And then the linear fit is not a very good approach to going there. So if you have less certain data, if you have noisy data out on the ends of your data sets, this approach might be give you a different, a less clean value than this approach. So all of that is just to say there's no one answer of a way to do this, and we practice different things in here, finding mean values, finding slopes of lines, and so on in order to do this. And again, always remembering that these things might not be linearly related, these two variables. So that's just a little bit of an introduction of ways you can make decisions to think about how you want to handle the data, and things you're going to see coming up in the lab book. And you can practice this as much or as little as it seems to make sense to you, the users of this book. But it is an important part of the process of taking data and turning it into a meaningful model. There's one other thing that shows up a few times here, and that is to say you might want to make a histogram of your data set And if you make a histogram of your data set, that is a plot of the number of values that fall, the number of measurements that fall between any two values. We just earlier today, I gave you an introduction to the distribution of star clusters on the sky. Got me to thinking about this a little bit. And there we said 0 hours of right ascension, 1 hour of right ascension, 2 hours of right ascension, 3 hours of right ascension, 4 hours of right ascension. If we had one that fell between 0 and 1, we would draw a dot there, boom, we got a histogram. And there's 2 and 3 and 4. And let's suppose there's 4 between 1 and 2. We would draw 2 points, one at 1 and one at 2, and draw a horizontal line across there and connect them that way. Suppose there's 3 between 2 and 3. We draw there, and boom. And suppose there's 5 between 3 and 4. We draw a point there and a point there. Oh, a little bit of parallax problem with my drawing right here. And we've got that value. But you've got a histogram. Maybe you've seen histograms before. So you're getting a histogram, and that's showing you the number as a function of the value that you're measuring across there. How many fall between in these ranges? And you can choose those ranges. I could have gone from 0 to 30 minutes of right ascension, and 30 to an hour, and an hour to an hour 30, or every 15 minutes, or I could have done every 2 hours or something along those lines. And you can make these histograms multiple times and see which ones look like they. If you overbend the histogram, so if you make smaller bends, there's so little data in any bend, you're dominated by noise. You're dominated by things scattering up and down, so you see all kinds of fluctuations that aren't really telling you anything other than you don't have enough data in a bend to see what's going on. If you make too few bends, so for example, if we made one bend that was 0 to 24 hours of right ascension, we would have 1 point, and that tells you nothing, right? It tells you that they're all on the sky someplace. Anyway, so you see that you have some flexibility in making the number of bends, and you should utilize that flexibility. If your data is clumped when you make a histogram, what you might find, suppose you're looking at all your distance measurements from a galaxy cluster. So you're looking at one cluster of galaxies, and you measure the distance with the Hubble law over here, and measure the distance to this cluster of galaxies, and you've measured 100 galaxies. And you might make then the distance, the number that fall between distances, every 0 to 10 megaparsecs, 10 to 20 megaparsecs, 20 to 30 megaparsecs, 30 to 40 megaparsecs, 40 to 50 megaparsecs, 50 to 60 megaparsecs. Let's do it every 5 megaparsecs. Okay, and so you might find that they all fall between it looks like this. And you get a nice clump right there. And so that's telling you this distribution is centered right here, and you can measure that center. And one of the things you could do is you could go in and fit a Gaussian to this distribution. And that's very, very non-susceptible to outlying data points. If you had outlying data points over here, this is a great way to find the mean of your Gaussian fit. So there are ways to use these distributions to find your mean right there, to say your uncertainty again is going to be the standard deviation of that fit divided by the square root of the number of data points that are in there. And so you can go as much or as little as you want into all of this stuff. But again, you might use the means, you might use some slopes. You'll see this come up again and again in different labs and different approaches that we're taking to doing this. And so this is just an introduction to some of the types of graphs that you'll see, and some of the very, very, very brief type of data, some of the data analysis that we'll do in this book. So that's a sort of, I don't know if it's helpful or not. That's sort of a very quick overview of thinking about what a graph is, a histogram, and an XY graph like this, and how we might use them in this textbook. So good luck with that, everybody, and be aware that when you see these popping up, where you're going to use these throughout the different exercises.